Yeah, so let me clarify before. I was after lunch. One of my friend actually accused me that I am joined Bajrang Dal, and it has become anti-romance is my now life's purpose. But this is not the case. So let me clarify. So this is a little bit inspired from a famous novella by Albert Camus, Stranger. The hero is a little bit self-doubtful and apathetic. So at the end of the day, he wants to do something good, but eventually he does bad. So we'll see one kind of protagonist like this. Okay. So introducing protagonist. So these are AI generated images. Don't take it seriously. So in the quantum world, it's very important that who governs the dynamics. Okay. So this H you can see on the left hand side. This is called Hamiltonian. Forget about that. It's like a astrologer in quantum world. Okay. So if you give a present state, it gives you the future, but yeah, only the catch is it gives it correctly. Okay, and there is on the right hand side, there is something called entanglement. I think what is written on the lower side, this is correct, and many people have tried to explain it by English language, and they have failed. I will fail too, but let me try. So what is this actually? So this is kind of relation, okay? So this is relation between two objects, and these two objects cannot be described individually in the sense. So when we talk about our childhood, there are some questions we can answer by saying the answer as my mom or my dad. But when we can say that who helped you grow, then the answer is parents. And the parents is kind of relationship where you cannot describe your mom and dad individually. So I think of entanglement in such a way, okay? So yeah, I know this is a very sloppy metaphor, but let's go with it. Okay, so these are the two main protagonists, and this is actually our anti-hero in the sense the right-hand side is our anti-hero. So, okay, so let's introduce the anti-hero. He is taking the central stage. So as a troublemaker, at the very first place, there are some companies who is actually trying to build quantum computer, and this anti-hero actually creates error in this, in the sense it makes problematic life for us in the sense. And then it helps also. So as a healer, he works it like, then it helps in error correction in the sense how the John Preskill says that you fight entanglement with entanglement. So yeah, so this is one. Another one is, it's a bit tautological, but still. So it makes classical computer inadequate to solve some quantum problems. You don't have to go to the serious. I'm just trying to emphasize the irony, okay, of this character. And it makes also quantum computer powerful. So it's tautological, but yeah, still get it this. And this is unstable, okay? So if you introduce some form of environment, it gets destroyed very easily, but it kind of brings stability, so-called topological order, but okay, let's forget about that. So what I want to emphasize in this slide is like, our anti-hero is try to do something good, but at the end, he does something bad. Okay, so on the right-hand side, it's a spatial resolution atomic spectroscopy, something called. So you can think of it's like the stock market in electron world, okay? So electrons, so in stock market we trade money, we trade stocks, and here electrons trade something else like charge, spins. But why should we care? We care because eventually if they trade, we'll get electricity, eventually we'll get magnetism, in the sense we will get good magnets. And maybe in the distant future, we'll get something like superconductor, or maybe, electricity without cost. We don't know, maybe. So yeah, that's why we should care. We should feel good materials, and that's why we should care. And finding the ground state is very important, because that's where the quantum phenomena is actually very predominant, in the sense you can see the quantum phenomena, so-called quantum phenomena, in the ground state. And it seems very hard problem, in the sense there are obviously a bunch of eminent classical computer scientists there, so obviously hard, I have to be very cautious when I'm saying hard. So Alexei Kitaev is the first person, just like a Kitaev style, he did not write the paper. In 1999, he just gave a talk, and then eventually he was kind enough to include this proof in 2003 in his monograph. So he showed that if you take a generic quantum many-body system, in the sense the stock market of electron world, then to eventually in the stock market also everyone wants to be happy. All traders wants to be happy. So electron also wants to be happy. Obviously they deserve it. And classical computer cannot find the configuration or find the condition based on which actually they are happy. Even what Kitaev proves that even quantum computer cannot do. Okay, so why, okay, so at the end of this slide, I think the message is we should care about electrons, how they are describing the dynamics and everything, and it's very important. Okay. So why is it difficult? Okay, the first question is why is it difficult? The difficult because, as I wrote it down, exponential growth of Hilbert, forget about that. So important part is like if you want to describe, so we have like billions of people. In electron, let's say we talk about only 50 electrons or maybe 100 electrons, the complexity grows very highly, okay? So it grows exponentially. So you can imagine how high this number is. So if you really want to describe a generic state of 100 electrons, then practically you need very vaguely I'm saying that this much amount of bits in your classical computer, and that is impossible. Okay, so then the question is, if it is hard, if Kitaev said that it is hard, then it must be hard. So now the question is why quantum statistical mechanics is so successful, okay? Hard condensed matter so-called is so successful to describe the dynamics of 100 electrons. So in naive term or in a briefly I can say the interactions are local. You don't have to understand that, but you can understand that a little bit from this picture. So here the electrons actually talks with each other locally, in some sense locally in the sense you just talk with your neighbor, you don't talk too far. And if you put this kind of condition, then eventually you get to see a very, so you get to see, yeah, so these are the very nice results. So actually there are a lot of results, I just, these are the reference I find it interesting. So I think, so people ask that, okay, quantum condensed matter is good and they are like, you know, they are very correct to predicting something which is matching with the experimental result. Then people ask why, okay, and the why result is actually this. So there are like techniques in, I have very rudimentary understanding, but these are the techniques in condensed matter. And these are the people who actually showed that, as I have written, that mean field theory is a technique. So this paper actually said that why mean field theory works, okay? Why is it a good approximation to study the stock market of electrons? And this paper on the nature of physics, I think 2009, it says that why quantum chemistry is hard. In fact, superconductivity, which is one of the, Hubbard model is one of the model to describe superconductivity, that is itself a hard problem to do. And DMRG is another algorithm which is also very successful. And people realize that, okay, this is something, some form of variational principle over matrix process, but those are technical terms. But the important point is there is some role of our anti-hero, it means of the entanglement, to describe the dynamics. And if your dynamics is hard or if your dynamics is easy to describe it in classical computer or be it quantum computer, depends on our anti-hero. Okay, so this is little bit of different side, but I'll connect those. So, you know, all of us use battery in some sense in our mobile, in our computer, laptop, or everywhere. So what is the most powerful battery we have? This is the lithium-ion battery. So what it happens, like, it depends on like 19th century physics or maybe electrochemistry. So something like ion, you know, running to each other, something like that happens, and you get charging, discharging in your mobile. Okay, so this is the most powerful battery, so-called classical battery we have in our world. So this is, I'll connect the previous slides with this one. But it has been pointed out that no, okay, this is not the end. We can, in fact, as we can build the quantum computer, we can build a quantum battery also. Okay, and these are the experiments which actually says that, okay, so if you have bunch of electrons that we have seen, like 100 electrons, and you hit them with a photon, and you eventually get some form of quantum battery. Okay, it has some advantages, we'll see. So in some sense, it has a good enormous power and low energy density, in the sense, if your mobile to get full charge of your mobile, if you need like 1 hour, then maybe it can take like few microseconds. At least that is the scaling, that is the very optimistic scaling. So in some sense, quantum battery is good. But yeah, here the anti-hero comes again, okay? So the entanglement comes again. So how the entanglement is relevant? It comes because it helps in the power of quantum battery. So as I told you that if your mobile battery is getting charged, full charge for 1 hour, it can give it in a microsecond for quantum battery. But the point is, the responsible element is this entanglement, okay? So entanglement actually helps us in quantum battery. But also it reduces reliability, in the sense, if you really want to, reliable, so you want to say that, okay, my battery will be charged this time within few microseconds, and you will get to see that no, this is not the case. On average, it will, but it may take few hours. So in the sense, there is no reliability in the charging or discharging time. So entanglement, again our anti-hero, okay, helps, eventually does not. So we asked the question little bit that what makes our quantum battery powerful, and we realized, in the sense, okay, our group in MSc, me and Shivashish mainly, but anyway, so what we realized that quantum battery, what makes quantum battery powerful is actually the kind of elements make quantum computer powerful too, okay? And there is no one candidate which can make the quantum computer powerful. There are there are at least 3 so far known, that entanglement can help, so-called non-Clifford circuit can help, swap can help. And the one important thing is about swap, okay? So this is kind of operation what you do on quantum computer, which is not entangling, in the sense it does not create entanglement, but it eventually gives you some form of supremacy over the classical computation or the classical computer. So yeah, so quantum computer, it's very confusing, the answer is very confusing, which gives the power, so-called quantum supremacy. As well as we realize that in quantum battery, it's also very problematic to address one single issue. But anyway, so this slide is more of an aesthetic issue, because I thought it's like, it's IMSC, so at the end of the day, people wants to see some mathematical expression. So yeah. So what we did, actually, we introduced another protagonist. So you have seen that how energy and entanglement kind of influence each other. So we want to introduce another protagonist because it was needed. It's not like I just wanted to include, that's why I included. So something called control complexity, okay? So what it essentially means, forget about those equations. So what it essentially means that if you have, let's say you can see the braces, right? The braces are on the 3 particles. So what this measure says, if you want to control 3 particles, this is okay, doable. If you control 4 particles, that is more hard. If you want to control 5 particles, that will be more hard. And how you can actually quantify this? You can quantify some mathematical technical jargon, but at the end of the day, what is our very small contribution to the literature, I guess at least, that we introduced another protagonist, which is control complexity, and we realized that, okay, this is also an important resource which helps us to build the good quantum battery, maybe in the future. So yeah, so if I really want to wrap up, and I want to say that what we did in our research, so this is the meme. So essentially people thought the entanglement is the only resource to generate more power, and we realized that no, it's not actually, it's control complexity. And there are few unanswered questions also, but yeah, let's see in the future. Thank you.
Any questions?
Okay, sorry. I should take questions. Yeah, sure.
You said entanglement gives stability.
Yeah.
Can you explain it?
Yeah, it's a long-range order. In the sense, it's a result from Bhastrate and I think Hastings also, but later Bhastrate had a PL about that. So if you have a long spin chains and you want to, so let's say you want to prepare the GH state, okay? So it's like it has a long range entanglement, in the sense long range order. So it is like people have realized that, okay, it is very stable under the local noise. If you have some form of local noise into the system, instead of the global noise over the whole spin chain, then your state can be very stabilized against the decoherence or something like that. So that is the stability.
This complexity, sorry, this
control complexity.
Control complexity.
Yes.
Is it somewhere related to some generalized definition of entropy or?
No, it's not exactly. It uses little bit of optimal transport in some sense. There is some mathematical, okay, entropy. I'm not sure if there is any connection. I have not thought about it, but.
It's the most generalized definitions like Rayleigh entropy or those kind of.
It's kind of distance actually. It's a metric in a control space. So.
Yeah, entropy is large.
Yeah, it's control. I'm not sure if entropy can be connected. Maybe. Well, we'll talk about it.
But entropy also helps in equilibration.
Yeah, it's more about non-equilibrium. It's actually not equilibrium in the sense you want your system to be in an excited state, and then when you want to charge, you want to put your system in an excited state, which has a lot of energy, and rather when you discharge, so you extract the energy out of it. So it's not exactly equilibrium systems, it's rather the non-equilibrium system. So in non-equilibrium system, defining entropy is a bit tricky issue. But I am not sure, maybe there can be some connections. I cannot just opt it out. Yeah.
So let's thank the speaker again.
Thank you.